Okay, hello and welcome to this video where we'll look at some of the sample questions involving the Doppler effect, particularly in sound or in situations where the speed of the observer or the source is not too far different from the speed of the wave in the medium. So sound is by far the most common example of this, but also maybe water waves might be another example. So here is a multiple choice question from fairly recently, at time of recording. Train approaches a station. It's emitting a constant note, a constant horn sound, constant frequency, intensity from its point of view, from the train's point of view. So the question is saying what does the observer experience as the train slows down? So it's not travelling at a constant speed. It's not travelling through the station. It's slowing down and presumably stopping at the station. But it's definitely slowing down. Well, you could try saying, well, here's the equation and it's a moving source, so that's the equation, and okay, so plus or minus, but you don't need to. What you need to remember is EU. Okay, so EU, high pitch to low pitch, and that's what's happening in this case. It's going from high pitch to low pitch. It doesn't go all the way past, but that doesn't matter. It's still going to start off a high pitch, and then as it approaches and slows down, it's going to go to a lower pitch from the perspective of the observer. So F-obs will decrease. It's going to be A or D. But is it going to be A or D? Well, that depends on the intensity. Now, the intensity will be perceived by the observer as the loudness. The more the intense, the greater the loudness. It's not a linear relationship for human hearing, but that doesn't matter. It's still going to be the greater the intensity, the greater the loudness, the lesser the intensity, the less the loudness. As the train approaches, the loudness emitted by the intensity emitted by the train from the train's perspective stays the same, and it's getting closer. If it's getting closer, then what the observer will experience is a louder note. Intensity will be increasing, and therefore the only correct answer can be D. Moving on. From an old 2014 paper, an older 2014 paper, let's look at a short answer one. This is a definition question. As of recording, the IB don't give so many definition questions, but they might do. So define what is meant by the Doppler effect. So let me go to 1 minute and 13 seconds in this clip, approximately.
It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Oops. Okay, so it's the change in the observed or perceived frequency when there is a relative motion between the source of the observer or when either the source of the observer is moving. So Sheldon had it pretty much right there. Now let's ask an actual calculation required question. A child on a merry-go-round, a carousel, moves with a speed of 6.5 meters per second along a horizontal circular path A, B, C, D, A. The station observer is at a large distance from the carousel. So this is like a top-down view, this picture. The child blows a whistle while moving from, and it's important to note exactly what positions are involved here, from B to D. So although the thing's going round and round and round, all we care about is the events happening from B through to position D. And the whistle will emit a sound of constant frequency, 850 hertz. So that is going to be the frequency emitted by the source. Speed of sound, 330 meters per second. To determine the minimum frequency of sound heard by the observer. So it's going to be, starting at B, going to be moving away. At C, moving across, and at D, moving towards. So the initial movement is away, and remembering E is when it's coming close and O is when it's going away. So the initial, the lowest frequency heard will be that initial frequency when the child is at position B. F dash equals FV over plus minus US. It's moving away. Moving away is plus when the source is moving away a stationary observer. So we take the equation, we plug in what we know, the for 850 hertz source frequency, 330 meters per second, over 330 meters per second plus the 6.5. Multiply all that out, you get 0.981. 0.981 times 850 gives you a new frequency of 830 hertz for 2 marks. Describe the variation of the frequency of the sound heard by observer. Well, it starts off at the minimum frequency, and then as it moves through C and D, the frequency will basically increase. Okay, from 830 hertz to, if you do the maths, 870 hertz, but that is in brackets, so the implication is that you don't really need to do that, although it is worth 2 marks. I'm not quite sure, but that's what the mark scheme says. Fundamentally, it starts at a minimum at B, then goes through at C. It will match the frequency of the source, so 850 hertz, and then at D it'll be slight increase in frequency as it comes towards you. Okay, thank you very much for your attention.